Hello Year 12, this is Mr. Lim again, and this is our third video on equilibrium. We're going to be talking about equilibrium expressions and constants. All right. So we're going to be talking about that and then how to interpret equilibrium constants and what kinds of questions you might have. These are some of the higher level ones, but we'll see how we go. All right, so what's the equilibrium expression? So you understand that at equilibrium, you're going to have equal forward and reverse rates of reaction, and you're going to have the number of particles the same in the reactants and the particles. So if the number of particles of reactants and the number of particles doesn't change, then the ratio between those two things is probably valuable information. So the equilibrium expression is a way to turn the concentrations of those reactants and products at equilibrium into a single number so it can be compared to other equilibrium systems. All right, so this one over here, this thing over here, is the way that we turn a equation into the equilibrium expression. Okay, so what happens you see is that the little letters here are the coefficients, and they turn into the powers for the particular chemical. Right, you see the square brackets here, that means it's the concentration of those chemicals, right? And then you notice that it is products over reactants. Okay, so let's try this one here, this nitrogen, hydrogen, and ammonia, the Haber process, which we're going to learn a lot about. Right. So this one here, we will look at the the products first. So the concentration of NH3 to the power of its coefficient. What's its coefficient? 2 over the concentration of hydrogen gas to the power of its coefficient. And, oh my goodness, this is terrible. This is not even a balanced equation. There should be no coefficient there. And the concentration of N to the power of its coefficient, which happens to be 1, and that's what that one is. All right, so you take the coefficients and you put them as the powers of the concentration, and I can't stress how much it's the concentration, not the number of moles, of the chemical, right? That equals K. Right, it also equals Q if it's not at equilibrium. And we'll go more about that later on. Okay, so that's how you would write that one. So let's go through the practice, okay? So remember how we said it was concentration, not number of moles. So it's really important to recognize that certain things can't have concentrations, like liquids and solids. And so in a particular chemical equation, we're going to ignore them. Okay, so here we have the ionization of ethanoic acid, right? And we see that there is a water here, which is a liquid, which means we're not going to include it in the expression. Okay, the expression is products over reactants, so we're going to go grab these products here, right? And we're going to say, okay, concentration of CH3COO minus, what's its coefficient? 1, so I don't need to do anything, over H3O plus, what's its coefficient? 1, so I don't need to do anything. And then over the reactants, and this is the only reactant there, the concentration of the ethanoic acid. And there's no coefficient again. All right, so that's the equilibrium expression. All right, so equilibrium constants then are the value of K that represents how much reactants and products there are relative to each other at equilibrium. So your equilibrium expression can be at a time where it's not at equilibrium or at equilibrium. All right, and so this value can show you how much product and reactants there are. So if there is a very high K, okay, it represents mostly products, because remember, if you have the products over the reactants and you have lots of products, right, you're going to have a very high value, right? If you have a low K, you're going to be mostly reactants, okay, because you're going to have lots of these down here. So a high number like 20 to 1, you're going to have a low value, less than 1. All right. So high value, lots of products. Low value, lots of reactants. So the equilibrium constant varies at different temperatures. This is due to the temperature affecting the forward and reverse reactions differently. Also, let's have to think about why that is. Okay. This is enthalpy, this is progress, Is this an endothermic or exothermic reaction? It's an exothermic reaction, right? So the forward and reverse reactions have different activation energies. Where are they on this diagram? They should be here and here. Which one is the reverse reaction rate, activation energy? The red one, right? So, oh no, I've dropped my pen. So, since they have different activation energies, they're going to be affected differently by different temperatures. And in general, we're going to be learning some other principles later, but in general, if you have a exothermic reaction or a forward exothermic reaction, when you increase the temperature, K becomes lower. For a forward endothermic reaction, if you increase the temperature, K becomes higher. K becomes lower, let's have a think about what that means. K becomes lower, are you going to have more reactants or more products? You're going to have more, what? Reactants. Okay, and here you're going to have more products. Okay, so you got to remember what happens when K high value, more products, K a low value, more reactants. Okay, so let's go explore that a little bit more. If you increase the temperature, both reaction rates are affected, both forward and reverse reaction rates. Are they both increased or decreased? They're both increased. All right. Which one is favored more though? Okay, it's the endothermic one is favored more. Why is the endothermic reaction favored more? So let's have a look at this. Okay, so let's have let's draw an endothermic reaction here. Okay, H progress. Oops. Okay, so that's a energy profile diagram. Okay, and then if I was to have an energy distribution graph for reactants and products, and let's just assume that they have equal amounts. Okay, well, now remember these energy distribution graphs, right? I don't know if I've been doing a very good job of teaching this, but you've got to start at 0, 0, then you go up, and then there. Okay. Okay. This one here, same. Okay. Oh no. Oops. What happened to that last one? There we go. Okay. So these are the reactants and these are the products. Now, the forward reaction has an activation energy which is quite high. Okay. So the forward activation energy is here, EA, for the reactants. The reverse reaction has a quite low activation energy, EA here. Okay, does that make sense? So if I have the reactants and the products, and I have different activation energies, but they've got the same number of particles, when I increase the temperature, the same thing's going to happen. Same distribution curve change. Okay, roughly. All right. So if I have the same energy distribution curve change, right, I can look at that there and that there, and which one has the greater change in thing, right? So now I may not have drawn this to scale, this may not be beautiful, but the idea is that it goes from this to now this, right? Which is a certain amount of change. This one here goes from this, oh, it's terrible drawing, to this. Right, but what we're actually looking for is the change here, here, okay, and what? Here. Right? So, in theory, what it's supposed to be, and I don't think I've drawn this very well, is that the change for this one here, this change here, is going to be larger than that change there. Right? If that change is larger, that means more reactions will occur, and therefore you're going to have the endothermic reaction is favored more because of that. All right, so that's the idea. This is actually quite high level stuff. You don't necessarily need to know this, but what you do need to know is, okay, that as you increase the temperature, the endothermic reaction is favored. If you decrease the temperature, opposite, the exothermic reaction is favored. Okay, so interpreting equilibrium constants. The value of K can be used to compare two reactions and their relative amounts at equilibrium. So here I have two acids, okay, ethanoic acid and hydrofluoric acid. I've given you both of their K values, and that's assumingly at 25 degrees Celsius. All right, which one is larger? Well, it is the 7.2 times 10 to the 4, and I hope that you recognize that it's because of this and not because of this. Okay, you've always got to be looking at this exponential part here, and you should see that the 10 to the negative 4 is much larger than the 10 to the negative 5. All right, so this one is larger. So here's a question: which one will have a higher pH at equilibrium at 25 degrees Celsius, ethanoic acid or hydrofluoric acid? Okay, so let's have a think. Hydrofluoric acid, you have a K value which is larger, which means that you will have more products in the hydrofluoric acid than you will have ethanoic acid at the same concentration. If you have more products, all right, compared to the ethanoic acid, you're going to have more acid. More acid is going to translate to a higher or lower pH. A lower pH. Now remember, pH is always opposite when you're talking about acids. The more acid you have, the lower the pH. That will always trick some kids. So please make sure that you are thinking, okay, acids, and it's talking about pH. Is it getting larger? Is it getting smaller? What does that do to the pH? Think a little bit harder. Okay, so I asked which one will have the higher pH, and it's going to be the ethanoic acid will have the higher pH because it'll be less acidic than the hydrofluoric acid at the same temperature and at the same concentration. All right. Changing K values can determine if a reaction is endothermic or exothermic. Okay, so let's have a look. A weak acid is heated, and the heating is found to decrease the pH of the system. Is the ionization of the weak acid endothermic or exothermic? So let's have a look. Heated decreases the pH. So a decrease in pH, that means that you have more acid. Okay? If it's more acid, that means that there's going to be more H3O plus. And in general, which that's a product. Whoops, product. Okay, lower pH, more acid, which means there's more H3O plus, which is a product in the ionization of weak acids. Okay, if there's more product, right, we know that the K value has gone down, no, up. The K value has increased. K increases. Okay, temperature is the only thing that affects K, but we'll get to that one later when we get to changing systems at equilibrium. All right, so the K value increases. If the K value increases when it's a increase in temperature, that means that the forward reaction is what? Endothermic. Okay. Hopefully you've written that down from before. Endothermic. Okay, so K value increases, which means there's more products, which means that it's an endothermic reaction. Okay, so that's the principles of that. Let's look at this one. Equilibrium expressions can be used to express the ratio of reactants and products. That's the expression. Sometimes labeled as Q. The equilibrium constant, which is always labeled as K, is used to express the ratio of reactants and products at equilibrium. So therefore, the equilibrium expression value, Q, at a time not at equilibrium, can be used to work out what's happening in the system. So let's take, for example, a system of what we were drawing before. You've got N2, you got a bit of H2, and you got a bit of NH3. Okay, now this is not at equilibrium because there's no NH3, right? So if I was to take the concentrations of this at time 0, right, the equilibrium expression value would be a value not equal to K. So Q at time 0 would not equal K. All right? So if the Q at time 0 is not equal to K, which means it's not at equilibrium, we can use that Q value. And remember that Q value is just the concentration of NH3 over H2 and N2. And then don't forget the coefficients. All right? This at T0 would actually be a very low number because you've got no NH3, right? And K might be, I don't know, I'm just going to make up a number because I don't know what it is, but let's just say it's 4. Okay, so this is a very low number. Let's just say it's 0. Okay, so Q does not equal K, and so therefore something's going to happen. All right, so let's have a look at another system. A system not at equilibrium is found to have an equilibrium expression value Q of 1.4 at 25 degrees Celsius. The same system is known to have an equilibrium constant of 0.85 at 25 degrees Celsius. Describe what will happen to this system as it starts to move towards equilibrium. Okay, so let's have a look. Q is 1.4, K is 0.85, and we can see that those aren't equal. So Q must go up or down. It must go down to get to the equilibrium constant, right? So Q must go down. Okay, so if for Q to must go down, that means you must have more or less what? Reactants or products? Which one? Q must go down. That means you must have less products. Wait, what? No. Yeah, less products, more reactants. Does that make sense? Q must go down. And remember, Q is the equilibrium expression, which is products over reactants. If it must go down, you must get rid of some products and add more reactants. And then you'll get closer to the equilibrium constant of 0.85. So if you have less products and more reactants, which reaction is that? That's the reverse reaction. Okay. So the reverse reaction must occur more than forward. And we will say that that would shift to the left because reverse reaction is shifting to the left. Or we can say that that favors the left, things like that. All right, we'll talk about that kind of wording in the next video as well. All right, the reverse reaction must be occurring more than the forward, and therefore you'll produce more reactants and less products, and then eventually you'll get to the K value of 0.85. All right, so that is interpreting equilibrium constants. We're going to go probably through this in class, but we'll see how we go. That's it.